yeah, for today's Frontier Condensed Matter Physics seminar series. So today we're actually very happy to have Jeroen van der Brink. He's absolute expert on doing altermagnetism calculations. I met him actually this summer in UK and read some of his most recent papers and find them to be intriguing in terms of future predictions in our understanding of altermagnetism. So for this particular reason, I invited him to give a talk with the title of Altermagnetic Anomalous Hall Effect Emerging from Electronic Correlations. So yeah, Jeroen, it's all yours. And audience that if anybody has a particular question, you can raise your hand or just on Zoom and open your mic and ask. And but it's potentially probably better to ask in the end. But you're welcome to ask in the middle. Yeah. So if you don't ask questions, please mute your audio so we can have a better recording. Yeah. Thank you so much, Jeroen.
Oh,
yeah, it's
thank
all
you,
yours.
Pinchin. Yeah. It's a pleasure to give this seminar online. I'll be talking about altermagnets and in particular work done by the people here on the screen. The names are on the screen. And I should mention Toshihiro Sato, Sonia Haddad, and Cosma Fulga, who are in Dresden at the Leibniz Institute for Solid State Physics, where I am too, and Fakhr Assad, who is at the University of Würzburg, where we look together at the altermagnetic anomalous Hall effect. But first, okay. What are altermagnets? And we know that there are different types of magnetic materials, magnetic order. We know, of course, ferro-magnets, parallel spins that orient below some TC. An antiferromagnet, there's an alignment of anti-parallel spins. And in the ferri-magnet, there's also up and down spins around, but they have a different amplitude. So there's a net magnetization in the system. In paramagnet, there's no magnetic order. And the question is, apart from these 4 states of magnetism, is there room for anything more? And recently, the answer was yes. At least that's by part of the magnetic community. It's argued to be yes, because there's an altermagnet. And I'll explain in the rest of the talk what an altermagnet is, but I'll give you a first impression here. In a ferromagnet, we have all spins aligned in a particular direction, which means that in momentum space, in the band structure, in K space, their energy bands are split. And if there is no spin-orbit coupling, one can assign a spin to each band. So this red band has a spin up, and this blue band at a different energy has a spin down. In an antiferromagnet, there is no net magnetization, and actually, in general, also no spin splitting of the bands. The bands are degenerate everywhere in momentum space, at least if there's no spin-orbit coupling. An altermagnet is different, and it shares some characteristics of an antiferromagnet and some of a ferromagnet. It shares the characteristic of an antiferromagnet in that there is no magnetization. The total net magnetization is 0 by symmetry. However, there are higher order distributions, or there's a spatial distribution of spins that is such that there is a splitting of the bands in momentum space. And this splitting of bands and momentum space is determined by the symmetry. And in that sense, an altermagnet looks more like a ferromagnet. Okay. Just briefly, before I start, we have done a lot of work on altermagnets in our institute. We looked at altermagnetic spin textures. We have looked at fluctuation-induced piezomagnetism in altermagnets, Edelstein effect, non-chiral altermagnets, chiral G-wave altermagnetism, and also optical properties of altermagnets. I will not talk about any of that now. Today, I'll talk about 3 topics about large-scale ab initio study that we did, about the already mentioned altermagnetic anomalous Hall effect, and I will briefly mention topology in altermagnets and tell you about the Weil nodes or the Weil physics and the Fermi arcs that we observed in chromium and timonite. Okay, let's start from the simplest possible magnetic ordering, which is a local ferromagnet. So I mentioned this two-dimensional square lattice where there's a interaction between nearest neighbors. The exchange constant is smaller than 0. I have a Heisenberg model, and the spins orient parallel. Now I know that the wave function in this case is invariant for translation by one lattice spacing. It's obvious. And as a consequence, immediately one sees or one finds that this system will have a total magnetization because there's a magnetization on one side that is copied to all the other sides, and therefore there's a net magnetization. So if I don't look at a local moment ferromagnet, but at a metallic or a itinerant band ferromagnet, the situation is similar. Actually, now I have bands, and the up band is at a different energy from the down band. So I have majority spin states that are occupied until the Fermi level, and a minority spin states that are partially occupied or less occupied. And the splitting of the bands is given by the exchange splitting, which is related to the atomic exchange interaction, so which is a large number in general. At least if you look at iron or nickel, this can be of the order of electron volts. And in the band structure, I have the same considerations of the wave function symmetry and also find a net total magnetization. Now let's look at an antiferromagnet. I have the same square, I consider the same square lattice, but now the interactions are antiferromagnetic and between nearest neighbors. So my exchange constant is larger than 0, and I have a standard two sublattice antiferromagnetic order, as is, for instance, the case in lanthanum 2 copper 04, the mother compound of the ITC cuprates. In this case, the wave function is invariant for translation by one lattice spacing, but also at the same time, I have to do a time reversal, or I have to flip the spins. And because of the time reversal or the spin flip that relates the two sublattices, the total magnetization of this antiferromagnet is 0. And as a consequence, there's a Kramers degeneracy at each momentum, as I will show you, or as I will illustrate in this view graph. So now, if I consider a itinerant or a band antiferromagnet, there is no splitting of the bands, at least in a system without spin orbit coupling, or if I do a calculation and do not consider spin orbit coupling. So I have spin degenerate bands, so the blue and the red band here overlap. I shifted them a little bit so you can see it, but in principle, there is a degeneracy of the bands, and the fact that these bands are degenerate, the up and the down, means that they are equally occupied, and therefore the total magnetization of this system will be 0. The total magnetization of a band antiferromagnet is, of course, also 0. Now let's consider a altermagnet, and this is the simplest altermagnet that I could come up with, it's a checkerboard antiferromagnet, where again I consider the local moments, so local spins. And I considered this checkerboard with antiferromagnetic interactions between nearest neighbors, as I did before, and now added ferromagnetic interactions between next nearest neighbors along this diagonal on every second plaquette. So this is the checkerboard nature of this model. And I could ask you, what is the magnetic ground state of this checkerboard antiferromagnet? And actually, the answer is really simple, because there is no frustration of antiferromagnetic order. These here in green, I have ferromagnetic bonds. So the two sublattice antiferromagnet will not be frustrated and will be the ground state of this model. So now, having an antiferromagnet, we could ask again, is the total magnetization zero? And just looking at this picture, you say, yeah, obviously the total magnetization of this magnet in this ground state of this magnet, the total magnetization is zero. I have as many upspins as I have downspins. But let's try to be a bit more precise and ask which symmetry enforces the zero magnetization of this antiferromagnetic ground state. And I would take the analogy with the antiferromagnet that I considered before and consider the translation of a spin from one sublattice to the other sublattice. So is the wave function invariant for the translation by one lattice spacing times time reversal? And that's actually not the case, because let's look at this spin here. It has this nearest neighbor antiferromagnetic bonds, but it also has these ferromagnetic bonds along this diagonal. And the fact that it has ferromagnetic bonds along this diagonal will be imprinted into the ground state wave function. If I translate by one lattice spacing and also reverse the spin, do a time reversal operation, then I'll get back, I'll get the downspin sublattice, but these downspins now have an interaction that is along the other diagonal. So this operation, translation by one lattice spacing and time reversal invariance on top of it, does not leave the wave function invariant. The diagonal interactions on the two sublattices of the antiferromagnet are rotated by pi over 2, and I have to account for that in my symmetry considerations. What gives me the invariance is translation by one lattice spacing times time reversal times a rotation, a 90 degree rotation of the lattice, in fact. So this makes the band structure very different. Let me note a few things, or let's recapitulate. First of all, I want to note that the magnetic order in this case did not enlarge the unit cell. Already without magnetic order, I had two sites in my unit cell because of the different interactions on these two sites, the different directions of the diagonal interactions on those two sides. This material has collinear magnetic order. This model has collinear magnetic order. Its magnetization vanishes by symmetry, and this symmetry involves crystal rotation. Now, if I look at a band structure or of such an altermagnet or a altermagnet in an itinerant picture, then I'll see that at a generic momentum, there is a spin splitting of the bands. And if I do a rotation, for instance, I rotate kx to ky, I get again the same band splitting, only the up and the down bands are changed. So this reflects that at a generic momentum, rotation does not leave the momentum invariant. So there is a splitting of the bands, except at high symmetry points. For instance, look at the center here, which could be the gamma point at k equals 0. At k equals 0, of course, rotation leaves the momentum invariant. So a rotation does do nothing to the wave function, and therefore, in an altermagnet, also at gamma, or in this case at gamma, the bands have to be degenerate. So there's, in general, no spin splitting at high symmetry points or high symmetry lines or high symmetry planes in the Brigman zone, because these higher symmetries can protect the spin degeneracy. Okay, so here is what I call fast and loose approach to altermagnets. Collinear magnetic order, magnetization vanishes by symmetry. This symmetry involves a crystal rotation. And this consideration works in the absence of spin-orbit coupling. It's obvious that if you have spin-orbit coupling, you cannot consider the rotation of spin and the spatial rotation independently. These are intrinsically coupled. And the symmetries that I talked about so far actually were decoupled spin and spatial rotation symmetries. And if you want to do this not in a hand-waving way, but rigorously, you will have to consider spin groups and combine these spatial and spin symmetry operations. Okay. The consequence of these three facts is a breaking of parity time symmetry, so a spin splitting of the bands in general. This is not only true for electronic bands, but it will be true, or it is true, equally so for magnon bands, for the excitations, the magnetic excitations of the system. Also, those bands are generally spin split. Important is, as I said before, that the spin splitting does not require spin-orbit coupling, and it is on the scale of the local exchange field, which is a large number, and for instance, 3D transition metal oxides, a number that in general is much larger than the spin-orbit coupling. Now, all that I have said before was not invented by me. The persons that actually coined the word altermagnets are Libor Schmeichel, Jairo Senova, and Thomas Jungwirth in this paper of 2022, and they pioneered this concept already in this preprint in 2019 that was published in 2020. So in their visual representation, here we have a ferromagnet in real space that has a Fermi surface that in generally has two parts. The Fermi surface of a ferromagnet has a majority spin and a minority spin part, and they are decoupled. They are different in general. If I have an antiferromagnet, then my Fermi surface is actually spin degenerate because all bands are spin degenerate at all momenta. But now if I have an altermagnet, where if I go from one sublattice to the other sublattice, I have not only to flip the spin, but also do a rotation of momenta or of the lattice. In that case, there is a up spin Fermi surface and a downspin Fermi surface that in general are non-degenerate. They are different and rotated and related to each other by a rotation. This is the case for a D-wave altermagnet. Then this rotation is actually 90 degrees. For G-wave altermagnets or for even higher order altermagnets, this rotation will be less than 90 degrees. Okay. So what is an immediate consequence of that, or at least hand-wavingly? It's interesting because in this altermagnet, I have a zero net magnetic moment, but I can have spin polarized currents. So the idea of that is as follows. If I have this Fermi surface, or these two Fermi surfaces of the spin and the spin up and the spin down bands, if I apply an electrical field along X, the velocity in this X direction of the up spins and of the down spins is in general different. So if I apply this electrical field along X, the up and down spins will be accelerated at a different rate, and therefore I will get a spin polarized, a longitudinally spin polarized current along the X-axis. If I apply the same field along the y-axis, I will get the same spin current, only of opposite sign. So one would be able to change the polarization of the spin currents by changing the direction of an electrical field in a system that has a zero net magnetic moment. Okay, so this is say theory or even conceptual theory. What about real systems, real materials? And the real material, one of the first real materials that was considered in the field was ruthenium dioxide. it's a bit unfortunate because it turns out that in bulk it actually has the zero magnetization, or if it has a magnetization, it's tiny. It has so therefore it's not magnetic. But if you look at its structure, it's perfect for an altermagnet. It has two sublattices. This is a rutile structure. And the two sublattices are related to each other by a 90-degree rotation of the oxygen cages, as you can see here. And at the same time, there's antiferromagnetic order. As I said, this is not the best example of an altermagnet, but if you look at the band structure, you see, for a ruthenium dioxide with a finite magnetic moment, you'll see that if you go along gamma X, there is a certain ordering of the bands, and the blue and the red are the spin up and the spin down bands. If you go to gamma Y, which is 90-degree a direction at 90 degrees from gamma X, there are the same bands, but with opposite spin. There's also another system is chromium antimonide. It has actually the same symmetry as manganese telluride, which is probably the altermagnet that's most popular in the experimental community. Chromium antimonide is a system that's hexagonal, that has triangular lattices, and there's a stacking of these triangular lattices along the z-axis. And the stacking is such that if you look, the order is such that you have ferromagnetic planes that are coupled antiferromagnetically. So here the chromiums are ferromagnetic in this plane and opposite direction in the next plane. Now, if you look at an antimony and look at the surrounding here and look at the antimony that's in the next plane, you see that they have to get from one ordering to the other ordering, you not only have to flip the spins, but also do a rotation, in this case by 60 degrees of the crystal to get from one sublattice to the other. And this actually leads to a splitting of the bands. Here you see the splitting, the calculated splitting, and this is actually the Fermi surface of chromium antimonide, which is it's a distorted barrel. And if you look at the magnetic the magnetization, the spin of the bands that make up the Fermi surface, you see that it is here spin up, then spin down, and if you go to the other kz along the z direction, you change from spin up to spin down. Okay. Is this measurable experimentally? The answer is yes. The spin splitting is actually observed in RPES. So RPES is light shining on the sample, or X-rays, or UV. And electrons come out, and you measure, let's say, the band structure. Well, in this case, you can really say that you measure the band structure because correlation effects are not very large. And for different incoming energy of the photon, you will measure at a different kz. And you see here that here's the calculation. For this value of the incoming energy of kz, there is no calculated splitting of the bands are almost degenerate, which you also observe. And for different values of incoming photon energy, there will be, you measure at different momenta, and you can see that there's the spin splitting of the bands. The spin splitting is large, is up to 1 electron volts. You see it more clearly here. And this is the same spectrum, but it's the second derivative of that spectrum. And you see clearly that there is this large spin splitting, which is consistent with other reports in the literature. What is different in our paper is that we pointed out that there are while nodes in the system. These produce Fermi arcs, and these Fermi arcs are we observed experimentally, or our experimental colleagues observed them. And just to give you one slide with a flavor how this works. As I told you before, without spin-orbit coupling, at high symmetry lines or planes in momentum space, the bands are degenerate. So in a altermagnet, there are large portions, lines in momentum space where the spin-up band crosses the spin-down band. Now, if you add, in addition, spin-orbit coupling, if you allow for spin-orbit coupling, which always is there, these degeneracies will split, and either they can gap out completely, the spin-up and the spin-down band can gap out completely, or they can gap out in some parts of the momentum space and not in other parts of momentum space. And this gives you a wild point and Fermi arc.
Jeroen, so for this wild point and Fermi arc, which presumably will induce anomalous Hall effect, in this particular case, in which direction of the anomalous Hall effect you should expect?
Okay, that's a good question. So, and chromium and timonite, which is special, in chromium and timonite, the spin ordering is as shown in this diagram.
It's A-type. It's A-type, yeah.
Yeah, it's A-type, and the spin is along the Z-axis.
Right.
And this is turns out to be, well, this is a high symmetry axis, and it turns out that in this case, the anomalous Hall effect is 0.
I see.
With spin-orbit coupling, also with spin-orbit coupling, the anomalous Hall effect is 0. If you would rotate these spins into the plane, well, the coercive field is way too big for in chromium and timonite, I think. But if you would be able to rotate these spins into the plane, an anomalous Hall effect would be allowed.
I see. Thank you.
You're welcome. If there are any other questions, then please go ahead. Okay, so there are these while nodes and this interesting connection to topology in altermagnets in general, in metallic altermagnets in general. So now I gave you 2 examples, rutile and with the rutile altermagnets with the rutile structure and chromium and timonite, manganese telluride, which have a hexagonal structure. The question we tried to address pretty early in the game is how abundant are spin-split antiferromagnets or altermagnets. And what we did is look at the database of 2,000 magnetic structures, measured that are measured magnetic structures, this database, and calculate or determine how many altermagnets we have. And it turns out we have to be 60. There are about 60. Nowadays, we know there are many more. But in the MagData database, there are 60 of them. And here they are. Some of them contain chromium, manganese, iron. There are cobalt ones, nickel ones, even cuprates that are altermagnetic. What we try to determine is a measure for the spin splitting. Saying that a system is an altermagnet is in principle a symmetry statement. And one would like to quantify, well, if it's an altermagnet, is it a useful altermagnet with large spin splitting or a perhaps not so useful altermagnet that has a tiny spin splitting? And we introduced 3 different measures that are plotted here. And you see that all measures more or less give similar results. Here, if you look at cobalt difluoride or nickel difluoride, which actually both have the same similar structure, you see that they have a large spin splitting. If you look at some cuprates here, you see that actually they have extremely low spin splittings. Okay. If there is a question in the chat, then let me know. Otherwise, I continue with the last.
Let me Warren Pickett ask you that do insulating altermagnet have useful properties?
Ah, that's a very good question. Yeah, what's useful, right? Um, well, one could say in insulating altermagnets, there is the analogy of a spin current, of course, but now the spin current will be driven by heat because they are electrically insulating. So in principle, a heat current will carry a spin, um, uh, the same as in the uh, uh, metallic or similar to the metallic altermagnets.
So how similar is it to ig? For example, ig, is known to have a very strong, spin transport properties, induced by heat.
What exactly? What do you say?
Oh, I'm sorry. Yeah, in spintronics community, many people does ig, right? I mean, the YIG.
Okay.
Yeah, YIG it's a ferri-magnet.
Okay, sure.
Yeah.
Yeah.
Yttrium iron garnet.
Yeah,
Sorry,
yeah.
I get so familiar with
Yeah.
YIG. Yeah. So that has a very strong, spin transport properties by
Yeah.
thermal gradient. So do you
Yeah.
expect that in altermagnetism, in insulating altermagnetism?
Okay. So, well, I mean, I guess for many reasons you cannot beat YIG for it's well established. It's the damping is very, very, very small.
Right.
So that are all special things, and I mean, people have worked on it for a million years, right? So
Yeah, 500,000 years.
half. Okay. So, I mean, I would not. So, the only thing, okay, what I find interesting is that there are conceptually new possibilities in the altermagnets, and by symmetry, you can drive spin currents that you can change the direction of the spin by the direction of the current. This is either, and this will be true also by magnon currents. The direction of the spin that is carried by a magnon depends on the direction of the propagation of that magnon. That's interesting a priori. If it's useful, I wouldn't be able to say.
Okay, thank you.
Okay. So to the third and last part is I go to the Hall and anomalous Hall effect. So the Hall effect is, of course, a very old phenomenon, and it requires an electrical field and a magnetic field that generate a current in the third direction. So I have my right hand, I have the magnetic field in some direction, the electrical field in the direction perpendicular to it, and I create a current in the third direction. So the external magnetic field defines the direction of the Hall current. And the anomalous Hall effect is conceptually actually quite similar, but now it's not an external magnetic field that determines the direction of the current, but a magnetization, the internal magnetization of a ferromagnet. So M defines the third direction. Still, I have the fingers of my hand, the magnetization, electrical field, and the current. In an anomalous Hall system, it is a bit different how the anomalous Hall effect is created. It's actually due to a finite Berry curvature. So in an anomalous Hall system, there is this Berry curvature, which is denoted by omega, which is a property of the electronic band structure that takes the role of the magnetic field. And it's related to the direction of the magnetization. So due to an anomalous contribution to the velocity, so here's the electronic velocity, this is the band velocity, and this is the anomalous part, which involves the Berry curvature. There is what you can call a Lorentz force in momentum space. So here you have a ferromagnetic metal. Suppose there is a magnetization pointing out of the screen. An electrical field is applied in this direction, in the horizontal direction, and now in the vertical direction, there is the current generated. So there's no magnetic field here, and the important object is the Berry curvature. Now, here's the question that I want to ask. Can a Hall effect occur in a system that has zero external field and zero magnetization? And you would say intuitively, well, I have my hand and I need 3 fingers. Now, one of the fingers is missing, so I don't know how to orient my hand. And it looks very difficult to get a Hall effect out of that. However, if you look at symmetry, the symmetry analysis tells you that, yes, you can have a Hall effect without external or a magnetic field or without magnetization. The only thing that's required is time reversal symmetry breaking. However, if you look at a little bit deeper, the time reversal times translation kills the anomalous Hall effect. And that's interesting because that's exactly the symmetry that altermagnets do not have. And indeed, altermagnets fit the symmetry bill to have a anomalous Hall effect. And the question we ask ourselves, that's great if it's symmetry allowed, but can we write down, can we define a microscopic model in which this altermagnetic Hall effect indeed occurs? And for that, these are the last 5-6 slides of my talk. It will become a little bit theoretical now. For that, we considered a honeycomb system where we have nearest neighbor hopping and also the presence of fluxes, which translate into the presence of next nearest neighbor hoppings. You will recognize the Haldane honeycomb model with finite flux for it. So we know that in the Haldane model, actually, if you integrate the Berry curvature over the Brillouin zone, you get a Chern number. And if you get such a Chern number, it means that there is an anomalous Hall effect. If you dope the system out of so that it's a metal, the Hall effect will still be there, only it will not be quantized. This breaks time reversal and has no spin, so it's not an altermagnet yet, but we will now work to get it into an altermagnetic model. So we considered instead a modified model. So the modified Haldane model is the same as before, but only the fluxes on one set of these triangles point in the opposite direction. So again, this breaks time reversal symmetry. There's no spin. And this model was considered first by Colomes and France in 2018. What we did now, take this modified Haldane model and restore time reversal symmetry by spin doubling. If you do this for the Haldane model, for the regular Haldane model, you get the Kane-Milly model. And the Kane-Milly model is famous because it is the first model that showed, or the model that actually showed that there is a Z2 topological insulator. So we consider a modified Kane-Milly model. And the Hamiltonian is here. It has nearest neighbor hopping, and this codes here encodes, this term encodes for the next nearest neighbor hopping, which is imaginary and reflects the presence of these fluxes. And here's the band structure. There's the gamma point. You see that the bands are degenerate, spin degenerate at K prime and K, where the Dirac cones are in graphene. And now we have a spin splitting of the bands. And K prime and K are actually have opposite splittings of the bands. Okay, so we have a spin split band structure. The Hamiltonian breaks inversion, but conserves time reversal symmetry. And what we do is now introduce spin-spin interactions in this form, which is an interaction between nearest neighbor spins of Ising type. If I do a mean field calculation of this model, we see that there is a gap opening. This is a topologically trivial gap. It's due to the sublattice symmetry breaking. And if I look at the Berry curvature that is generated, I see that the Berry curvature of the bands close to zero energy have the same Berry curvature. The total Berry curvature of this band complex is zero. There is as much positive as negative Berry curvature. So this is a topologically trivial band. It doesn't carry a J number. However, if I have this band and I dope it, I will remove electrons, remove charges of certain that carry a net Berry curvature. In other words, the system that's left behind will also have a net Berry curvature, and therefore it will have a net anomalous Hall effect. So Berry curvature is generated, and doping causes a filling of bands such that there is a finite net Berry curvature present. So this is a mean field, and the two questions one needs to answer now is this model an altermagnet? And is this physics present? Does this scenario also hold in a many-body system? And the answer to both those questions is yes. I will not go in detail. If you have questions, then let me know. I can talk about it. But the upshot is that if you do a quantum Monte Carlo calculations, which Toshihiro Sato did, we find ordering. So it is an altermagnet. And you have a spontaneous breaking of time reversal symmetry, and an anomalous Hall effect does appear. Okay, why? The altermagnetic anomalous Hall effect emerges from the electronic correlations in this interacting Kane-Meili model. And where is my thumb pointing? Well, the thumb is pointing along the direction of the sublattice magnetization. This is the third direction. So it's the spin on the A sublattice minus the spin on the B sublattice. And that defines the direction that in turn defines the anomalous Hall effect. So then it's the Néel pseudo vector that takes the role of magnetization or takes the role of magnetic field for this altermagnet. Okay, my conclusions. Altermagnets are a new type of antiferromagnet with spin split electronic and magnonic bands. We have a substantial number of candidate materials. Metallic altermagnets are scarce, but they are interesting, as the question of Warren implied. Altermagnets are predicted to have interesting properties for spin charge transport, spin heat transport, piezomagnetism, anomalous Hall conductivity, Weil semi-metallicity, magnetic domain structures, magneto-optics. And today I could only cover a few of those interesting properties. Thank you for your attention.
Thank you, Jeroen. It's a very, very nice talk. Yeah. So let me, I mean, are there any questions from the audience? I have some questions. Okay. Yeah, please. Who raised his hand? I didn't see. Can you unmute your microphone and ask? Someone raised. Okay, let me ask you then. The question I have is, can you go back like 2 slides?
Sorry, can I go back 2 slides?
Yeah, 2 slides. Yeah.
Okay, I'll try to do that. Actually, I don't know how to go back here.
Yeah. For this particular material, you argue that your calculation basically suggests that your anomalous Hall effect will be highly dependent on which direction the Néel vector is, right? I mean, there's a tremendous amount of literature in the case of manganese tellurium, in which people have argued, probably including you as well, that depending on which direction the Néel vector is, in one case you would expect anomalous Hall, in the other case you would not. Can you actually explain that in a more sort of a naive way, so experimentalists like myself can sort of understand the microscopic reasons for why that is the case?
Hmm, that's I would almost say no, but it will be you'll have to look at the symmetry,
I see.
and if if the nil vector is along a symmetry axis, you might be in a case where you have a number of mirror symmetries that
I
are,
see. I see.
and if in that case, so that depends on the combined symmetry of spin and lattice, right? So it's not generic. It depends on each system. And if you have those mirror symmetries, and they might act such that this excludes anomalous Hall connectivity. So the good part is that if you manage to get the spin along, in an arbitrary direction, there will always be some anomalous Hall effect.
Well, I mean, according to your theory, and basically, even in the case of no spin-orbit coupling, you would still expect a little bit, ferro-magnetism, right? Basically, associated with time reversal symmetry breaking.
Yeah, so that's yeah. So let's say altermagnets are defined for in absence of spin-orbit coupling.
Sure.
Without spin-orbit coupling.
But
And now
every
there
real
is a
material
kind
has,
of
right? Yeah.
yeah. So there is a kind of a conceptual difficulty there because anomalous Hall effect will require spin-orbit coupling, at least in collinear systems. So in a collinear system, you need spin-orbit coupling in order to. So you are already talking about a system that's not, in the strict sense, an altermagnet anymore.
Right.
And if you break that symmetry, then normally also you allow for in the magnetic ordering for Jelesinski-Muraya kind of couplings, and these DM couplings can generate, or will in general generate the symmetries as such that the DM couplings will generate a small ferromagnetic moment, and at the same time the system will have a anomalous Hall effect. Actually, in chromium and timonite, the DM does not tilt the spins, and for the same reason, chromium and timonite does not have an anomalous Hall effect. So these two things are intrinsically related.
Also, because the chromium antimonite, because the moment is along C, basically DM interaction is not allowed.
Exactly.
I see. That's
an anomalous Hall effect for the same reason.
I see. That's very good.
They always come hand in hand.
Yeah, thank you very much. Any other question for Jeroen? We have still about 10 minutes left. Well, your talk is, I don't see any other hands raising up. Your talk is so clear.
Okay, how chemically perfect do these need to be?
There's a question. Okay, so from Matt, eager to say, how chemically perfect do these systems need to be? What about accidental doping?
Yeah, so that's a good question. Well, one problem is actually not as much the chemical doping, but the domain structure. So
Right.
so the fact that the anomalous Hall effect is depends on the sublattice magnetization, means that if you change the domain, also the sublattice magnetization changes direction. So if you have two domains present in equal amounts, you will have the anomalous Hall effect of them tends to cancel. So that's something you want to get rid of in the first place. And I would say doping in general, as long as it doesn't change the magnetic ordering and doesn't change the symmetry of the magnetic ordering, it does not play a role in itself. In manganese telluride, of course, doping is very important in order to get from a semiconductor into, or get from an insulator into a semiconductor regime. And in that sense, of course, you need charge carriers in order to get an anomalous Hall effect, right? So there it's essential.
Yeah. Okay. Okay. But in the case of a manganese tellurium, I mean, there are actually experiments suggesting that you can tune the spin direction from the in-plane to c-axis by lithium doping, done by guys at Oak Ridge National Laboratory. So would you and then expect that in this case there's going to be no anomalous Hall period in the lithium dope sample?
Right.
Okay, so that's your expectation.
It might be, yeah.
Okay. Okay.
Yeah, I was reading. Go ahead.
Warren Pickett had another question from a non-expert. Is there an anomalous spin Hall effect in insulating antiferromagnet? Has that been done, as far as you know?
That is really there in insulating ones there is not. I think we worked on actually non-collinear altermagnets with Mangli Hu, Maya Fagnori. And they showed that actually you have a spin Hall effect in those systems. But those are non-collinear altermagnets, and that's a whole different set of considerations there.
Actually, there's another question from Nitin Kashwa. Do you expect anything interesting by whole electron doping altermagnetic insulators, like superconducting tendencies?
Oh, okay.
That's an exotic question.
So I would say a priori not, or I don't think they're okay. Let's say, doping any antiferromagnets is interesting, and getting the metallic is interesting, especially the spin 1/2, of course. But actually the cuprate lanthanum 2 copper 4 is an altermagnet. Only the spin splitting is really tiny. It has to do with the rotations of the octahedra. But
are there actually evidence? Are there direct evidence for it besides theoretical evidence? I mean,
no. So I didn't calculate. We didn't calculate the spin splitting of the magnon bands there, but I would expect them to be beyond measurable. But we should do it and see.
Yeah, people have done spin wave for years, right? Like O'Dear and Stephen Hayden. Yeah. Okay.
Yeah. Oh, yeah. No, they should be split, but probably on such a small scale that it's not observed.
Okay.
Yeah.
Any other question for Jeroen? Okay, if not, yeah. Thank you so much. I mean, it's a very, very nice talk. It will be posted. I'm sure there are a lot of people interested in introduction, and all the other, very nice part.
Okay.
Yeah.
Thank you very much for having me. Thank you.
Thank you.
Bye-bye.
Bye.